Kia ora and welcome to video 15 in the series Insightful Integration. This question here is a little bit sneaky. We've got this region that's inside a square with curved boundaries. All points inside a 2x2 square that are closer to the center than the sides. When we're talking about distance to the sides of the square, we mean at right angles. So it's kind of obvious that if you take a point that's on one of the curvy bits that you just go straight towards the square. It doesn't refer to taking the normal to the sides of the boundary. You're taking the normal to the sides of the square, if that makes sense. Okay, because the closest distance between 2 points is the straight line between them. The closest distance to a line is the perpendicular distance. And I'm talking about the perpendicular line to the line. Hopefully I haven't confused you there. Give this a crack. Of course, there are no equations in the question itself, so you'll need to form some if you're going to use integration to solve this problem. All the best, and we'll catch you after the intro music for the solution.
Okay, so the trickiest part of this problem isn't really the integration, but actually the realization that the boundaries of this region are parabolas. And I'll show you two ways of deriving the equation of these parabolas. Once we've got the equation, the rest of the problem is pretty straightforward. So first up, we need a coordinate system. So if I just make my x-axis this bottom boundary here, and the y-axis will go straight through the middle of the region. Often we like to exploit symmetry in problems like this. The reason why it's a parabola is because there is a definition, and if you look it up, it'll give you better wording than I'm about to give, but it's a parabola is a set of points that are equidistant, that the distance from a fixed point to this parabola. The reason it's a parabola is by definition, a parabola is a set of points that are equal in distance from a fixed point to a fixed line. And this line here is called a directrix. And the fixed point here is the focus. And that is what a parabola is. It's a set of points that those distances are equal. And when we say distance to a line, the directrix, which happens to be the x-axis in this case, is a line, we mean perpendicular distance. Okay, so those two things are true. If we consider an equation of a parabola, the one that's on the formula sheet is y squared equals 4ax, and that's a parabola that opens up to the right if a is positive. Our one opens upwards, so it's an x squared equals 4ay one. X squared equals 4ay is one that opens upwards or downwards depending on the sign of a. So if a is positive, then the focus is at the point y equals a. Now our focus is at the halfway point, y is equal to 1, but the distance, but the vertex of this parabola is halfway between, so the distance from the vertex to the focus is therefore a half. So your a value, which is the distance from the vertex to the focus, your a value is a half, and so we've got x squared equals 2y, and we also know that the parabola is moved up. It's moved up a half from the x-axis, so if we have y equals a half x squared, which is the rearrangement of x squared equals 2y, then we need to add a half to it. And that there is the equation of the parabola that we have. And of course we could consider the other sides as well, but we don't need to find those equations if we are just using the symmetry of the shape. So how do you find that equation if you don't know anything about directrices or foci? So from the problem itself, it says a region consisting of all points closer to the center than the sides. So what you could do is just call this point here xy, and we say, well, we don't know its equation, but let's call it xy, and set up a right angle triangle here and work out that distance, not the half, because the half is half was the distance from the vertex to this fixed point, the focus, but just there, that right angled triangle has a height of, bear in mind that it still cuts through there, this is still y is equal to 1. If my x-axis is the bottom of the square, this length here is 1 minus y, and if I make my x-axis still down the middle of the shape, then that's x. So we've got, by Pythagoras, 1 minus y squared plus x squared square rooted is the distance from the focus to the point xy, and then the other distance, so that's that one, the other distance that we need has a height of y, right? It's just the y value from the bottom to the point xy. So those distances are equal, and if we square both sides of that, we get 1 minus y all squared plus x squared equals y squared. And if we then expand those brackets, the y squareds cancel, and if we rearrange the equation, we're going to get y is equal to x squared plus 1 all divided by 2, or half x squared plus a half. So you get the same equation using Pythagoras as you do using basic parabola knowledge. Okay, now what do we need to do? We need to find some area using integration. Okay, what I'm going to do is find this area here, which means I need to find the point of intersection between the bottom parabola and the one that's on the side. Now I could find the equation of that side parabola, or I could just realize that that line that I've just drawn here, the diagonal, has a slope of minus 1, and it goes through this point here, which is 1, 0. So this equation, this line has an equation of y equals 1 minus x, and then we want to equate that to the parabola a half x squared plus a half, and we solve that equation. That will give us our limits, and we find that the appropriate limit we want is square root of 2 minus 1. So if you solve that quadratic equation, this limit here is root 2 minus 1, and that's 0. Okay, so to find that green shaded in region there, we're just going to integrate between 0 and square root 2 minus 1. The parabola is the top part of it, and the bottom part's just the x-axis, so we're just integrating the parabola, half x squared plus a half. Okay, and that gives us a sixth x cubed plus a half x, between root 2 minus 1 and 0. Okay, and we could we could work this out in exact form, but I don't think it's going to be particularly nice, so let's just work in a decimal format. Gives you 0.2190 to 4 decimal places. New graphics calculators give it to you in exact form as well. Apparently it's minus 5 plus 4 root 2 all divided by 3. But unless the question asks you for the exact area, then I'm not so worried. What does the question ask? Find the area, not the exact area. Okay, so we've got that. We've got the total area of the square is 4. It's a 2 by 2 square. And we've got 8 of these regions, right? Because we'd have another one there, 2 on either side. So 8 of those regions, plus we've got 4 corners in here, which would make up the whole outer region. And what is the length of that? It goes root 2 minus 1 across, so it's 1 minus root 2 minus 1, so this will be 2 minus root 2. Okay, you can check that, 2 minus root 2, and you add root 2 minus 1 to it, you get a length of 1 there. So the squares 2 minus root 2 all squared. And then so we're taking that off the big square. So the total area of the shaded region is the total square 4 minus 8 lots of what we just found. I'll just work with the decimal format. Minus 4 corners, 4 squares of 2 minus root 2 all squared. It comes out to be 0.8758. Again, if you've got an updated graphics calculator, then it will give it to you in an exact format. Minus 20 plus 16 root 2 all divided by 3. And that's the answer to the question. Hopefully you found that quite nice. Like I said, 2 ways of finding the parabola. You didn't really need the knowledge about directrices and foci, but it did help. And then realizing a coordinate system, like setting up a good coordinate system, is important. One that's going to help us make the integration simple, and we use the symmetry of the shape to mean that we didn't have to calculate too many things. Catch you in the next video.